I'm very happy to introduce Antonio Capone as our next speaker. Antonio is coming to us from Politecnico Milan, and he's also
I borrowed your pointer.
CTO of a startup, MobiMesh. He has extensive experience in all areas of networking, including protocol design, traffic management, engineering, wireless routing. And so today, though, he's going to... What?
So many things, because I'm getting old, right?
And on a personal note, he's been very welcoming to me into the Italian networking community, so I'm very grateful for that.
The family, right?
So today I think he's going to be presenting to us a very exciting technology called OpenState, which I think will be very interesting to a lot of researchers here. So,
Thank you, Robert. Thank you for the introduction. Yes. Yeah, the talk is on the data plane. So I will try to use some of the concepts that Holly introduced also to try to shorten the presentation, right? So the idea is to take a look at the evolution of the data plane, and I will honestly I will use a more restricted definition of SDN. So I will stick more on OpenFlow and what exactly is the evolution within OpenFlow and how it's changing, right? So this is a joint work with some colleagues from the University of Rome Tor Vergata and of course some of my students in Milan. And this is also part of a European project, BEBA, which is behavioral-based forwarding, and the project somehow is based on this idea of the OpenState that I will present to you, even if in more general framework. So this is the outline, and following the suggestion of Marco and Robert, I will try to write some questions. And the first question is, really how far can we go in the evolution of the data plane and the abstraction of the data plane? And as I said to you, I will try to give our answer and our approach, which is based on this idea of OpenState, where you create stateful data planes, retaining somehow the properties of OpenFlow and the type of abstraction that you have on OpenFlow. The second question is more an open question, and it's really for the expert of programming languages, how to incorporate this kind of statefulness in the data plane into the programming languages, and how much of this should be exposed to the programmers, or must be somehow hidden in the compiler. So let me start with, again, setting the scene. I will be short really and focus on OpenFlow and try to also to follow what has been presented by other speakers, try to focus on the real key questions that we need to think about. So you know everything about the classical networking paradigm. We moved away from with SDN, and the reason is that, of course, you have distributed functions and you have state distribution, which is our standard protocols for control, but of course you have proliferation of these standards, and of course you have closed platforms with limited programmability. So mainly for these two reasons you move to SDN, right? So the SDN paradigm is, again, breaking this horizontal architecture of traditional networks and make it vertical. But still, you don't get rid of the problems that you have, because intrinsically the physical system is distributed. So you create this architecture where you put this smartness in the control. You take out the control from the devices and you make them dumb, and then you create this smartness in the controller in order to control the network. But of course, in order to do that and to enable then the abstractions that you use for programmability, you need to expose this data plane abstraction to the controller, right? So again, it's important to understand here that OpenFlow and all the protocols that are for the southbound, they are not only protocols, they are really abstractions that you use in the controllers for controlling the device. And the compliance with this, the devices to the abstraction is fundamental, both for compatibility, of course, and the compatibility is a problem here exactly like it was for the distributed world, but also because somehow you need to avoid destroying the business of the manufacturers of these devices. If you ask them to expose too much, they will never follow you in the creation of the ecosystem, right? So again, we may have different opinions on that, but for sure SDN is not a new idea, and there have been a number of attempts in different directions. But for sure, we will not be here without OpenFlow. So OpenFlow is for sure the rule changer in this domain, right? And if you remember the paper that proposed OpenFlow, well, it was meant to be a clean slate approach, right? And at least in principle, that was the idea, right? But if you look carefully, that's not the case at all, right? It was not a clean slate approach, basically because it was a very pragmatic approach. They try to understand what are the capabilities of the commercial hardware platforms and try to find out the compromise, pragmatic approach in order to expose these functionalities to the controller. So creating this abstraction was done based on a compromise. And as I said, it's hardware platform, and also Colin mentioned a lot these constraints coming from the hardware platform. So in principle, you can say, well, okay, do we really need to have hardware switches? Well, in principle, you can do a lot with soft switches, as we know. And what is actually contradiction here is that SDN has been designed and defined having in mind the hardware constraints, but actually it was much more successful with soft switches than with hardware, right? Which is actually the problem that we have today, right? So in any case, we will continue to have this kind of capacity difference in magnitude in the different implementations of whiches, and this is gonna be there.
Is that 10x performance per watt? That's what is it performance per watt, performance per dollar, performance per?
It's capacity basically.
Right, but capacity I can always fix if it's right. I can always scale out, right?
Sorry?
I can always, like, if power constraints and dollar constraints aren't a problem, I just buy a rack of machines. Right?
Sure, of course, that's true.
So
but okay, but then you need somehow to compare in dollars then,
yeah,
right?
Yeah. And are those? Do you believe those differences are true if you go to dollars or per watts?
Well, I of course I know I'm not an expert. But there are several people assuming that this. I mean, if you assume that everything can be done in software with general purpose CPUs, of course, the story is completely different. At the moment, I mean, at least the kind of evolution that we are witnessing is because basically most of the solutions are based on dedicated hardware, and we cannot live without them. So I mean, you can argue if these differences are real, but still there are some differences, right? So, and again, talking about the abstraction, then the abstraction that was proposed at the beginning was the flow table. And the flow table is very, very simple, match actions and statistics for the counter. So I will not spend time here, and I just want to point out that the match is not the general match, while in principle it was, but actually it is on a set of specified fields in the packet header, right? Not an arbitrary field in the packet header. And I will come back on these. Well, in the end, you can say, well, okay, but you mentioned about the abstraction and the real hardware, right? So, in principle, a flow table is very similar to TCAM. So, well, okay, that was the idea. You have the flow table and you have TCAMs, and that's the parallel between hardware and, well, of course, it's crazy to think that the flow table can be implemented with a single TCAM. What is really true is that you have a pipeline. And pipeline is specialized, so you have specialized stages for different type of packet headers fields, and this is the reason why you cannot make a match on an arbitrary field. And this is also the reason why when you move from OpenFlow 1.0 to OpenFlow 1.1, they tried to mimic this one with multiple match tables, but of course, this abstraction is much less, of course, flexible than this one because basically you now have very specific assumptions on the way this is mapped here, right? And this is the reason why you can not think to this just a way of using some flexible resources here, but typically you need to consider the different stages that are specialized. So, as I said, and also discussed before, it's not particularly satisfactory, right? So you in principle you have a fantastic model, and the model is very ideal. You can match on any field. You can define your own protocol. But in practice, as I said, matches can be done only on specified fields. The actions are extremely limited, and the manipulation of the packet that you can do is extremely limited to what is already implemented in the other platforms that you have, right? So as a result, today OpenFlow is not really protocol independent at all. Okay, the protocol means data plane protocols, of course. And standards, of course, are still necessary. So you can see that the evolution of the standardization of OpenFlow is including many new headers every year, and this is, of course, making even the standardization and the definition of OpenFlow extremely complicated, right? However, and again, here we can have different opinions of that, but there is a trend, and the trend is in defining more flexible hardware platforms. Okay, it's not completely clear if this will be successful, but there's a fact that there is a huge interest in the definition of and a number of also of implementation that prove the feasibility of these approaches to create pipelines that are really configurable, right? Okay, programmable. Well, let's say configurable is probably more appropriate, right? Which means that you can really create a parser that is able to make the match on the field that you define, okay, with the description of the parsing program that you can write. You can use global states to influence the behavior here, and what is more important, you can define logical stages using the hardware resources that you have without being constrained to have a specific amount of resources in each stage. So this is, and finally also you can also have a little bit of flexibility, not too much really, in the definition of the actions and the kind of manipulation that you have in the packet header when you rewrite some components, right? This is, as you know, the well-known proposal by McEwen and others, by Giese and others, in SIGCOMM 2013, reconfigurable match tables, and there is a lot of interest and also somehow business activity behind this kind of hardware platforms, right? So when you now have something that is a pipeline which is programmable, then of course you need something to program it, to configure it. And P4, that also Colin mentioned before, is exactly for this purpose, and not surprising, almost the same people are involved also in P4, right? So P4 is now growing up, and they launched a more public initiative this year. The idea is that basically you can use P4 for defining the way you manage your hardware, and then you exploit this configurability of the hardware while you can continue to populate the rules for the forwarding with classical OpenFlow. And of course you can do that controlling the different components, and also even splitting between ingress pipeline and egress pipeline. An interesting part is that you have some kind of reconfigurability here, so some kind of dynamicity. So it's not really programming in real time, or it's not really a control plane, right? It's not, the control plane is still based on the OpenFlow abstraction, but you have flexibility in the definition. You create the device, and you support the different functions in the device. Okay, so but even in this kind of, you can even question and argue if this is real and it will fly. But even in this kind of approach that is somehow this OpenFlow 2.0, as McEwen said, you still retain the same abstraction of OpenFlow that was proposed since the beginning, right? So in the end, you still have a stateless table or set of tables where you define the way a packet is forwarded, right? So. And just to mention, there are other similar examples here that have been done on using the same approach, right? Yes?
Doesn't P4 have the notion of metadata or tags that you can associate and that's kept locally?
Well, the metadata is always possible, right, to associate, and then of course tag pushing and these kind of things. These are possible in any case.
Metadata is usually state within processing a single packet rather than across packets. There is limited memory space in sort of in the P4 model, or in the RMT model. They have some space set aside, which is supposed to be sort of for global, few registers, but I don't think it's, and I know it's unclear, but I think there is state in the RMT architecture, they do mention state. They do have some set of global registers.
Well, yes, you can configure the stages exactly, these global states, and these are somehow metadata that you associate permanently or even.
Well, but you can rewrite them as part of
Yes.
a pattern action of a packet, which can enable you to maintain state, right? Like you can store state there, right?
Yeah, you can store, but not in this part of the pipeline. You can not go back to the global states. At least this is my understanding of this architecture. So global states must be somehow configured by the P4, for example, which means that you have the dynamicity that you can have with P4, but not with OpenFlow or with the packet, processing, individual packet processing. I mean. Okay, so. So the question here is now, okay, so this is the limit. So this stateless approach with flexibility, okay, that we can introduce with P4 or similar approaches, but still we have just a list of rules that will be followed in order to process a packet. So can we introduce a little bit more smartness in this data plane? That's the point, which means some more dynamicity, so that we don't want to go back to the distributed world still, but see if it is possible, retaining the general approach, to introduce some capability of processing in the switch. So the real question is looking for the right abstraction. Of course, you can find in the literature and a number of projects, practical projects with prototypes, experiment deployments, where you can push a lot in the direction of programmability. And if you even think back to the history of pre-SDN like active networks and forces, you will see that they failed mainly because they pushed too much into the data plane programmability, right? While OpenFlow, which sticked only on control plane programmability, it was successful, right? So really, it's difficult to try the right balance here. Otherwise, really, you can just make another academic proposal, which may be the case, of course, but without really any chance of being considered and received by the community of the manufacturer. So the key words for the success has been so far pragmatism, compromise, and right mix of programmability and level of abstraction. So that's in the end the way we have made SDN getting out of the labs, academic labs, and getting into the real network, right? So in OpenFlow was a compromise actually, and the main problem was to persuade commercial brands to expose this abstraction and make the things fly, right? And which means that they expose something, but they don't open their box. That's fundamental, right? If you get rid of the space for manufacturers for the optimization of their own hardware, basically you are destroying their business, and of course this is something that cannot be well received. At least if you want, they collaborate, right? And of course the compromise is that you maybe don't push too much toward the programmability, but still you have something that can be implemented and optimized by the different manufacturers, high performance, low cost supporting, right? So consistent with the idea of vendors to have closed platforms in the end, right? This is true, right? Maybe in the future we will have commodity hardware that will be completely so cheap that nobody will make business on that and make business on everything else. But at the moment, this is not the case, and probably.
I don't know of any vendors that think that their hardware is. I think this is. These arguments were critical for getting OpenFlow to be adopted. I think that they hold a lot less water now than they did then, which is to say that the currents are, almost no networking vendor looks at the current industry and says, white boxes, that's never going to happen, and we're never going to have to worry about that. Everybody is sitting looking at white boxes and basically saying, the question is, how long can I put off having to switch to that model? Not is it going to happen?
Yes. Not easy. If you think to reconfigure match tables, they are a little bit pushing in that direction of making the hardware so flexible that in the end it has no value. That's the point. If the hardware is extremely flexible, in the end, producing it has no value in terms of business. That's the point, okay? Which is the risk, right? Because if you go in that direction, you destroy one part of the industry related to networking, right? Okay, so, and the point is that OpenFlow forces the separation, and this is because of the abstraction. So you force the separation, and you have this, again, every time remember today, logically centralized control. So you have the which is the spark part, and you have the switch which is dumb, and then you get events from the switches, topology changes, traffic statistic, arrivals of packets that are forwarded to the controller, and then the controller can send commands, install and uninstall rules, query statistics, send packets, and whatever, right? So this is the approach. What are the pros and cons? The pros is that, of course, you have central view of the network, which is used today by all the languages that are built on the northbound interface, and you can use network states. So with this global view will allow you to simplify the dynamic management of the network with dynamic policies, right? You have one-click network configuration because you have, in principle, platform agnostic protocols, even if, of course, we know that it's not completely agnostic, but still, in principle, this is an advantage. The cons is, of course, control latency, right? And you in any case, in whatever is your implementation of the control of the controller, in the end, you have some latency in the control part, which may not be a problem for most applications, but is a problem for a number of networking applications. And 1 second of delay is a huge amount of packets that are dropped in today's high-speed networks, right? So the central view is then a great idea if you have to manage applications that require the big picture and decisions based on the global view of the network, the global network status. It's not actually a good idea, it's a poor idea in case of local states with local decisions. So if you have states that can be managed locally, well, probably it's better to do that in the switch without getting to the controller. So the division is then to try to a little bit move a little bit of smartness from the controller to the switch. Not too much, again, but a little bit. And try to see if it is possible to inject simple programs that are able to characterize the behavior of the switch, again, using the same concept of rules, but changing the set of rules that are applied based on a state. That's, in the end, the simple idea that is here. And in the end, that the control is still centralized, so which means that the programmability is still based on this central approach, which is the core idea of SDN, and the decisions are global, but only for the states that are global. So you get notification to the controller, but you can react locally, and so the controller can retain the global view of the network. But in the end, you delegate the execution of small part of the application to the switch when this is related only to local events and different forwarding behaviors that you can pre-program in the switch. And of course, this is the advantage is clear. You don't have the delay of getting to the controller for taking decisions.
Local control programs are not nanoseconds.
Sorry?
The packet forwarding time is nanoseconds. Local control time is 20 microseconds.
Okay.
If you want to go, I mean, not that it's still the same general idea. It's a lot faster, but it's not. It's 3 orders of magnitude.
Yeah, probably. I mean, we have to set the idea, right?
It's 6 orders of magnitude.
We push a little bit, and that's fine. So again, said in another word, with the classical approach, you have global states and local states in the controller in any case. So you have all the notification of events coming from the switch to the controller, and all the control that is enforced by the controller, right? So you can do something similar, but again, you delegate a little bit of the control for those events that are local to the switch, and then you get only notifications for the states that are global and notification for the change in the local states that must be notified to the controller just for retaining consistency in the global execution of the application, right? Which means that, okay, we made both the controller and the switch smart, but of course, the level of smartness here is extremely limited and completely controlled by the controller. Okay, well, okay, this is easier said than done, because in the end, I said to you, well, how, right? I mean, why is it's not just another, well, maybe, but it's not just another proposal that, well, the idea is that you need to really stay on the type of requirements that you have. So we need something that can be really high performance, which means that it is able to process the events at the speed of the data plane, so the interfaces of the switches, and independent, again, exactly like OpenFlow from the platform of the vendor, and viable somehow on most of the hardware platforms that are available, right? So apparently, this is very beyond OpenFlow switches. Well, our finding, and probably this is a surprising finding, is that in the end, the solution is much closer to OpenFlow than you expect. And it's really small modification to the abstraction of OpenFlow, and the implementation that you can have in the hardware is really based on the same approach of match tables that you have in OpenFlow, right? So the idea, as I said to you, is named OpenState. These are some references. This is the first paper, and there are others detailing some of the characteristics of the proposal. And I will give you a link to the project, so you will have there all the papers and presentations, even more detailed presentation than this one. So let me introduce the idea with a very simple example, maybe stupid example, but it is an application. The application is the port knocking firewall. So the idea is that you have a firewall which is instructed to drop all packets, okay, including the SSH port 22 packets, okay. But if a source is able to send a sequence of packets with a predefined port numbers, then the switch will open the port 22 and will allow the packets to go only for that source, of course. Okay. So what this means that you receive the first knock, and then you move to the next stage. Then you receive the second knock and move to the second stage, the third stage, and finally you open the SSH port. So this is of course done, and every time you need to follow exactly this. If you just fail in one of the stages, you come back to the original, to the default stage, and then of course forward the rule. Okay. So how would you implement this in SDN, right? And with OpenFlow? Well, basically you drop all packets. Well, not really, because you need to forward the packets, encapsulate and forward the packet to the controller, and the controller has to maintain the state of this knocking, very simple knocking sequence, and only once the state is the open one, the last one, then it will instantiate a rule in the flow table in order to open port 22 for that specific IP source, right? So you can imagine, right? Even in this very stupid application, you forward a huge amount of packets to the controller. So this is of course not made to process a large number of packets, right? So lots of overheads, of course. See, easy, right? Can we move the state machine in the switch? Well, in this case, it's completely local, right? And the events making you move from one state to the other one is basically the arrival of packets with specific port sequence in the switch, right? So this is something that is the type that you can move in the switch, right? How? Well, in principle, you can try to create a table, okay, like this one, okay, and this is basically a flow table with some metadata, which is a state. Well, you can retrieve the metadata from some database, and I will show you that the database is a table itself. And then you receive the packet, you add this label, which is your metadata, you look at the table, you find your depending on the stage that you are, and then you perform the action. Well, you see here we have two actions. The one is the forwarding action, drop or forward, and the other one is next stage. So you need to next stage. Sorry, you need to somehow go back to the state database and write because this is an event for your machine, and write something in the database. Okay. Well, the point is, can we turn also the database into a table? Well, this is possible as well. So putting together, what you do is that you have two stages, the state table and the state machine table. In the state table, you have the different flows, and you store the information, the metadata referring to the state of that specific flow in this specific application, right? So you get a packet, and you look at the state table. You look with the IP source, in this case, a key, and this is the key that you use for at the ingress of the packet in order to look at the table. Then you find your line, and then you associate the metadata in the next stage. You put it in the second stage. You look at the second table, and then you get your actions. In this case, is drop, and then the next state is open, right? So then we need then to write into this table, and this is the only difference that you have in a two-stage pipeline of SDN. Of course, you can argue this can be complicated, but what we did is we implemented this with some hardware, and we proved that in the end, the complexity of this look back for writing is not that complicated. So in the end, what you see here is that you have defined the state machine into the switch, where events for transitions are still of the type of the matches that you use for flow tables, okay? But you use the information that you have on this kind of events in order to change the behavior, the set of actions that you apply to the specific flow. What is also more interesting is that here we just have the state machine, and the behavior that you have in forwarding depends on the state, not on the flow. And then you have a large table for the flows that will give you only the state where the flow is. Okay. Again, it's simple, but can illustrate how it works, right? Sorry. Yes. Well, of course, there are some extensions here, right? For example, you think to Mach learning was one of the examples that others presented today, right? In the case of the Mach learning, actually the event is related to another flow, not the flow that is being forwarded, but the one referring to the source Mach, right? Well, it's not much different in the end, so you can define cross-state handling, because one event which is detected when processing a packet of a flow can actually change the state of another flow, modifying the entry for the other flow. So you just need to modify the field that you select for the right action, and this is something that can be included into the table, because you can define the way you extract the key for the right action, exactly like you define the key that you use for the read action when you read the state table. So as I said, we implemented this idea both in software and in hardware. So for the software, this is public domain. There is this OpenState -sdn.org site where you can find the software and the number of mininet applications that have been developed. The port knocking, of course, is the simplest one, but several others. We also have an hardware implementation which is described in this paper. Actually, the matches are the type of events that I use in my example. Well, actually, you have other events that can be processed locally. The one is time, of course. You can use timers, and this is particularly powerful in a number of applications. You can have all flow states that are also very powerful, because you have a state for a superset of flows, and this can be even crossed with the per flow state. You can have meters and many other ways of locally handling events. The instantiation, of course, can be done in many different ways. So you can have a number of different state machines that can be based on different set of flows, so they are parallel, or you can even combine in a serial way the different machines that you have with multiple stages. So coming to the last part, and very briefly, because of course languages are not my domain, as you understood probably by my presentation, right? So everything is then now under a different light if you look at the data plane like something that can be stateful, right? So the question, and somehow open question, is how to incorporate statefulness in the languages, right? Well, let's think to the stateful application that you can define. So we did a number of applications. Port knocking is the one that I mentioned you. Mark learning, we work with reverse path forwarding, flow consistency for TCP flows, failure recovery, the DDoS, and a number of others. Some of them are already on the web page. Others are currently being checked for the public release. We are also working on some more challenging applications, of course, related to TCP flow processing, monitoring application, and others. And these are not easily mapped to the type of architecture that I show you, so we need some extra logic, and this is mainly the focus of the European project. But how we did it? Well, we did it with a custom implementation in the controller, right? Using the capability that we have in the extension of the OpenFlow switch. So we know what can be done by the switch, and in the controller we manage to use the capability of the switch with these small modifications of the OpenFlow protocol in order to implement the application. But this is of course something that does not scale, and you need some kind of incorporation in the languages. So let's pick an example, and this is probably the most well-known example, which is frenetic pyretic, right? How do you manage dynamicity, states in a language like this, right? Well, you know that you can define your network policy with parallel and serial composition of elementary policies, and then you have your policy enforcement, which is done through the compiler that was discussed in another presentation, which translates everything into a set of overflow commands. So this is the way you enforce your policy in the network with an outbound abstraction like pyretic, right? But then you can also have some instruments for querying the network status, getting notifications on the network status, and then you have this policy dynamic adaptation that can reconfigure the policy, okay? And then if you reconfigure the policy, then you of course reinforce it. So you have this kind of adaptation, which is actually the dynamicity that you incorporate in the language. So the states somehow, and the handling of states in the network is here, right? And somehow also included in the Python language by itself, right? So the open question is actually, how can we use this stateful data plane in the languages? Well, an easy solution could be, well, let's create a library of switch state machines, and then let the language be able to use this library of state machines, simply instantiating these machines in the switches. This is probably the easiest way of retaining the same global view of the languages that you have today and use it, right? And of course, this is constrained to the number of functions that you can define, the number of state machines that you can put in the library. But can we see also some mechanism for an automatic discover of the local state machine starting from the global network policy? Can we just look and analyze the network policy and identify the machines that can be actually moved to the switches because they are local? This is basically a parallelization of the computing, right? So you try to delegate part of the computation, and again, as you know, is in the classical parallel computing problem, you need to find a way to split the task and parallelize it, right? Another question is how much of this parallelization must be exposed to the programmer and how much must be somehow hidden in the compiler. All these are open questions, but in my opinion, they are particularly interesting, and I think that the language community can contribute to this kind of research trend. Okay, thank you very much for your attention.